So for this block, it's really a continuation of the theme from the previous block. And we're going to use a little script that is very similar and modified. But I want to just address the question of reliability of measures, which is often overlooked. So variation in your measures isn't always bad, but it depends on the question you're asking and the source of the variability. And so if you've got variable measures, it could be between you because of variability, heterogeneity in your participants or your animals. Could be moment by moment fluctuations, or there could be technical issues or experimental bias. And these are things we've already touched upon. In most experimental contexts, you want to minimize all those sources of bias, and people will often want to use fairly homogeneous groups of subjects or samples. In observational studies, you might be interested in individual differences, and you may want to maximize variation between individuals. If, for example, you're interested in what causes reading problems and you've got some theory that it's some sort of auditory problem, it wouldn't be any good if you only studied children who were all very good readers. You'd want to have a spread of scores, for example. But you need to distinguish that from moment by moment fluctuations. So you want to be sure that you're not just picking up variation that the child's in a good mood or a bad mood, or that the list of words you're using is really not one that's very suitable for their age or whatever. What you really need to be clear about when you're picking a measure is whether it's got reasonable test-retest reliability. If it's got a lot of variation, but that variation is all due to just sort of slop, if you like, or noise, error variance, it's not going to be a good measure. So this is just simulated data for a vocabulary test, but if you had the same person tested at time 1 and time 2, you'd have to think to yourself, well, which measure would I want to pick if I was doing a study with this as my dependent measure from, say, an intervention trial? And you can see that you've gone from a reliability of about 0.8 to about 0.56 down to just below 0.4. And clearly that last measure is going to be much less good as a dependent measure. But quite often we just don't have that information about our measures, and people don't see it as important to establish reliability before launching forth into a great program of research. I would argue in most cases it's really important to establish reliability and actually do a little study where you literally do test people on more than one occasion, or animals on more than one occasion, to get an idea of really just how good the reliability of the measure is. Because if it's low, your chances of getting a sensible result are reduced massively. So I just want to show you how reliability can vary depending on how many items you've got. So I'm just going to show you this simulating item script. This time it's exactly the same as a script we used in the last block, but instead of 5, we've got 9 observations for each participant, because we can then compare how well different observations agree. That is, in effect, the test-retest reliability, depending on whether you've just got a single observation on each of 2 occasions, or whether you've got one based on the average of 2 or based on the average of 3. So if we go to the script, it's a simple little script here. I won't go through it because you can go through it at your own pace, but it's essentially identical to the one we had last time, except I've now got 9 measures of blood pressure in this case. And then I work out these averages, which is slightly different. The average is based on pairs of measures. So we've got 3 possible pairs. We've got measures 1, 2, and then we've got measures 3, 4, or measures 5, 6. And then here we've got averages based on trios. So observations 1, 2, and 3, 4, 5, and 6, 7, 8, and 9. So these are independent from each other, but they're simulated using the same formula. And what you then see is what are the correlations between these different measures. So if I just run this whole script and then pull this up so we can see things, this is a set of correlations between individual measures, and they're in a range of about 0.5. They're healthy, but they're not huge. But if we then average together 2 such measures, and then we've got 3 of these pairs of measures, the reliability is now getting much better. It's 0.7 odd. And then if we average 3 together, it goes up even higher. So this is just making the point again that the more data you put into a measure, all things being equal, provided you're not then seeing habituation effects or some fatigue effects or whatever, more data is going to give you a more reliable measure. And you definitely need a reliable measure if you're going to get sensible results. So let me just say, and that's just the script. This is something that people in psychology, in some fields of psychology, are very, very well aware of. Fields called psychometrics, where you're measuring cognitive abilities or personality. These are sort of things that you're taught about when you're making up your measures, and people go to some length to ensure measures are reliable, usually. But there's other areas of psychology and other areas of biomedical science where this is not appreciated at all, and people will just sort of pluck a measure from the air or make one up without really checking whether it is reasonably reliable. If you move to measures of brain structure and brain function, there are studies of reliability of these. Interestingly enough, people tend to assume that they will be reliable because somehow they've got a physical reality to them. But of course, that's not true with brain function in particular. You can get a lot of variation from one occasion to another. And even brain structure measures will vary, in part because of technical reasons, but also they can actually vary from one occasion to the next, depending on, for example, position in the scanner. And where reliability has been evaluated, it doesn't really make you feel terribly confident that these are necessarily good measures. So my recommendation is, if you're picking up a measure that you want to show interesting correlations with other variables, and it doesn't correlate with itself on a different occasion, it's not going to be very good at correlating with anything else. That sets an upper limit as to what you can expect to see. This was pointed out some years ago now. This was 2009. This is a paper that made it into the Scientific American, called Voodoo. I think the title was a good one, Voodoo Correlations. And it was to do with people showing in brain scanning experiments correlations between behavior and results of functional or even structural imaging that were just too good to be true, because the correlations between a measure of brain function and a behavioral measure were higher than the test-retest reliability of the behavioral measure. And that's impossible. And this was used to point out that a lot of p-hacking was going on, that people were measuring many different things and then just plucking out the correlations that looked good. So this brings us full circle back to p-hacking from the first part of this course, that if you have got high evidence of high correlations between things that are not actually reliable, it's actually diagnostic that somebody's been doing p-hacking. So this is the last slide. I think it would be interesting for you just to identify popular measures in studies in your own area and check, does anybody know anything about their psychometric properties, in particular reliability? There are other psychometric properties as well, like sensitivity and validity, but reliability is a particularly important one. And if you're not sure, have a go with Google, or look on Scopus, Web of Science, or Google Scholar, using reliability in a keyword search. And you might be surprised, there might be a literature on this that just people tend to ignore. Nobody might have looked at it. If reliability is known, it'd be very interesting to see how good it is. Quite often where studies are done, they're not really done with enough people. You need really samples of 50 and above to start getting a decent estimate of what reliability is like. But, and for more reading around this topic, Dubois and Adolphs wrote a very nice paper on looking at individual differences in fMRI, which for those of you who might work in that area, I would say that's a very good read. Sam Parsons, a postdoc in experimental psychology here, has also got his fingers burned trying to do studies with measures that turned out to be non-reliable, despite being very widely used in psychology. And he ended up writing this nice piece with some colleagues on how we need to be reporting on reliability, and how if we don't have that evidence, we are likely to be fooling ourselves about results that we get. But I hope that I've convinced you that you can study all of these things with simulations, and they give you a sort of confidence that you know what you've put into a simulation and you can check out what comes out the other end. So you don't just have to trust somebody else telling you that you should do this or you should do that. You can check out what the consequences are for different decisions in your experimental design and in your analysis. And better still, I think you can start to get an intuitive grasp of things that otherwise might seem just a bit difficult to do anything other than, memorize without really getting any detailed knowledge of what's behind what you're learning. So I hope that simulation will liberate you to become much better scientists in that regard. But please make notes of questions or make notes of topics you'd like to cover in an interactive session, and I'll do my best to answer them, although they may be beyond my capabilities. Thank you.